send you the notes that we're going to be taking. The first thing I want to talk about for enzyme kinetics is Michaelis-Menten. Okay, so enzyme kinetics. The first thing we're going to talk about is enzyme kinetics. Oh, everybody send me their emails. I like it. And if you guys want to take notes, I should be going slow enough for you guys all to take notes, either on your iPad or on a piece of paper. If you're going to do pen and paper or pencil and paper, make sure you get some colored markers as well. Is everybody good to go? Or should I wait just a couple more minutes for you guys to grab those things? Pen, paper, colored pencils.
I'm good to go. I don't know about the rest.
And again, you don't need to take the notes today. I'll be sending these notes if you don't want to do that. Just be an active listener. And then I'll have about 4 questions towards the end. A couple passages, a couple questions at the very end for those that decide to stick around. Okay, so let's just get started. So the first thing we're going to talk about is Michaelis-Menten. Okay. For the MCAT, you do need to know Michaelis-Menten.
I don't think we can see your screen.
You can't see my screen?
No. It says the stream is paused.
The stream is what?
There you are. I can see it now.
Can you see it now?
Nope.
Oh, there. It's off for a second.
Oh, that's weird. Okay, so if I minimize Discord...
I think you're just sharing your application, not the whole screen.
Okay.
So you just stream the Discord to us.
Let me stop streaming and then let me maybe try to fix that, okay?
Sure.
Round 2. Let's try it again. Oh, I see. You're absolutely right. I was screen sharing the channel. All right. So, everything good? Everybody rejoin? All right. So, looks like I was screen sharing the app, not the screen. Okay. So the first thing you guys got to know is Michaelis-Menten. This is a high yield topic in the BB and even the CP section. So you can find it in 2 different sections, and by extension, that makes it high yield. When we talk about Michaelis-Menten, you need to know the equation. Does anybody know what the equation is? What is the Michaelis-Menten equation? Any thoughts? Okay, I'm going to assume that silence means I'm not quite sure. So the equation you need to know for the MCAT, and I recommend that you probably throw this on an Anki card, okay? So make an enzyme kinetics deck and throw this equation on there because you will need to know for the MCAT. And the equation is V naught, or the initial velocity, is equal to Vmax times the substrate concentration all over Km plus the substrate concentration. So you will need to know that.
A quick question. So I actually knew the equation. I didn't know the name of the equation. Do we need to know for the MCAT the name of every equation, or just knowing the equation is enough?
Just be able to recall it or recognize it. I don't think it'll be very obvious when you see it in a multiple choice.
Okay, but like you probably would need to know the name of the equations.
No, you don't need to know the names per se.
Okay. Thank you.
It would be a benefit, sure, but do you need to know? But if you get a question like on hydrostatic pressure, then you better recognize what that equation might be, right?
Okay.
So whether you know the name or not, well, I think it'd be a benefit. Is it necessary? No.
All right.
But certainly will help. So I kind of jokingly say that this is the big booty equation. Okay, so I'm not kidding, big booty, because it's kind of a fat bottom equation. Okay, and if we were to outline this you can kind of see it's kind of like a big booty snowman. Okay. And the reason why it's a big booty is because we have multiplication on top, and the multiplication in the numerator kind of condenses this numerator, right? Where if we look at the bottom, the denominator, the plus sign kind of expands that out and gives that big booty persona. Now that sounds silly, okay? But I think it's worthwhile knowing that, jokingly or not, because it's going to help us remember whether multiplication or addition is on the bottom. I think that's half the battle in remembering this equation. Okay. Now we'll come back to this equation. I'll throw some more tips up here how to memorize this convoluted equation. But for right now, I want you to think of this as the big booty equation because it has that plus sign in the denominator. It kind of expands everything outward. Okay. Now, one thing you need to also recognize on the MCAT is what Michaelis-Menten equations look like. Okay. So simply, if we have a graph or a plot, the Michaelis-Menten plot is going to look something like this, where you have the substrate concentration on the x-axis, and you're going to have the initial velocity, v naught, on the y-axis. Now, if we were to just graph the enzyme kinetic of just the enzyme, it will look something like a parabola, parabolic in shape. And so this is E, this is just the enzyme itself. And pay attention, right? So as we move to the left, or excuse me, to the right, we move to the right, the substrate concentration is going to increase. And as the substrate concentration increases, as we move towards the right, this enzyme is going to reach saturation. And as the enzyme reaches saturation, it starts to kind of horizontal off. And as it horizontals off, it approaches a term called V naught. It approaches its maximum velocity. The enzyme cannot go any faster because it is saturated. So this is known as V max. Now that's one term you need to know. You also need to know what Km is. Does anybody know what the definition of Km is? Or can anybody look it up and tell us what it is?
Half the concentration needed to reach Vmax.
Good. Yep. And what else? What does Km actually measure? So you're right. So 1/2, right? 1/2 the Vmax, that blue line on top. Right? If we were to extrapolate that out, okay, maybe I'll do that in a different color, actually. Maybe I'll do that in green. Right? Let's say this dot right here represents 1/2 the actual Vmax. And if we draw a straight line all the way down, that would be where Km is at. So what does Km measure? Besides this mathematical equation where Km is equal to 1/2 Vmax, what is Km? What does that mean? What does it really measure? Anybody?
Isn't it like the not efficiency, but like how good the thing is?
Close, yeah, I like it. So it measures the affinity, right? The affinity of an enzyme. Okay, and we'll talk about this a little bit more. So Km, yeah, mathematically it's 1/2 the Vmax, but it's a little bit convoluted, right? Technically, it measures the affinity. The smaller the Km, the stronger the affinity. Okay, so it's that inverse relationship. If you have a high Km, you have a low affinity. Okay, so it's back. If one's up, the other one's is down, and vice versa. Okay, so let's talk about when we have an enzyme with an inhibitor. Okay, so let's draw another line. We'll do some red now, and let's assume. In fact, let me draw this a little bit differently. Let me draw this a little bit higher, so there's not a lot of overlap. We draw this in between. And this red line is representative of the enzyme plus an inhibitor. And so in this case, what do we notice? Well, we notice that the Vmax, right, this blue dotted line, moved down, right? The inhibitor, in this case, in this example, moved that Vmax down. Okay, so we say, okay, Vmax went down from its original position, with just the enzyme in black, to the red. And then the question is, well, what happened to our Km value? What happened to the Km value? Any guesses there? Did Km go down? Did it go up? Or did it stay the same?
Up.
Say again, I didn't hear you.
I think it went up.
Okay. Does anybody want to support that or refute that? Any other guesses?
I think
What'd you say?
either it's the same or it went down.
Okay.
It depends on the kind of inhibitor.
Well, it depends on the kind of inhibitor, right? But based on what I've drawn, okay, so I'm only showing one example, one kind of inhibitor. I'm not going to draw all of these. But in this case, the Km actually stayed the same, right? So the X value, right, this is the X-axis, the Km value is still the same for the red, right? It's still in line on the X-axis as we move up, right? Still the same Km value. The only thing that's different is that the 1/2 V max value has changed from when we use an inhibitor, but the Km value is still the same. Kind of strange, right? So in this case, Km did not change, and we'll talk about this a little more. So if you're a little confused about this, don't worry about it right now. I promise you, it'll all make sense by the time we draw competitive, non-competitive, and uncompetitive here in just a little bit. Okay. So this, when you've got Km as not changing and Vmax going down, this would be an example of what's known as a non-competitive inhibitor. This is a non-competitive inhibitor in this example. And again, if you're like, wait a minute, Kevin, how do you know that? Well, we'll get to that. Sit tight. Okay. A little bit of prelude. If there's some deer in the headlight looks, that's okay. We're going to move on and get into the nitty gritty now. Okay. So, Michaelis-Menten, V naught is equal to Vmax times substrate concentration all over Km plus the substrate concentration, right? That big booty equation. And it's a big booty because we have that plus sign on the bottom. Simple as that, okay? Keeping it a little bit dirty to help us remember. So, that's all nice and dandy, but this equation is kind of rough looking, right? That is a big equation, okay? It's not very pretty at all. And in fact, the argument could be made that this equation was simplified to the Lineweaver equation. So Lineweaver is just a different format of the Michaelis-Menten out of necessity because you could argue that calculators at that time period were not very powerful. They could not do these complex calculations. So out of necessity, there was a need to simplify this equation to the Lineweaver format, okay? And so what we're going to do right now, okay, is we're going to go through that math. I'm going to show you mathematically how to go from Michaelis-Menten to Lineweaver. So I will preface that this will be a little bit dry. I know math isn't very sexy. It's not very jazzy, okay? But bear with me, okay? It's worth, once we get through that little Everest, it's going to be smooth sailing, okay? It'll be worthwhile. And so just going to sit up, perk up, okay? Humor me for a couple minutes with the math, and then I'll show you, right, how to maybe cheese some of this and how to remember it a different way. But I understand that some students are more math-centric. Most people probably are not very math-centric, right? But we also got to learn how to crawl before we run or walk, okay? So let's get through the not fun part, and then we'll have some fun with this. So Michaelis-Menten, convoluted, right? And we want to simplify this to the Lineweaver equation. And so let me write that down. And these are just different forms of the same equation. So Lineweaver, the Lineweaver equation, okay, is also known as the double reciprocal equation. The double reciprocal, okay? And I think that's a big hint here of what we're going to do. And the double reciprocal just means that on each side of the equation, we're just going to flip everything over on its head, okay? And the reason why I want to do that is because when we do that, when we flip everything over its head, we're going to get this equation into a straight line equation. We're going to get it into y equals mx plus b format. And that's going to be a lot easier to calculate, arguably, than what we have right now. So let's do that. So we're going to have, well, we originally have v naught. And like I said, we're going to take the reciprocal of each side, hence double reciprocal. So we actually get 1 over v naught. is equal to Km plus the substrate concentration all over Vmax times the substrate concentration. Okay, we flip everything over. Now, the next step we're going to do is we're going to expand on this. We're going to take this fraction on the right-hand side of the equal sign, and we're just going to expand that out. We're going to make this into, instead of having one fraction, we're going to make this into two. And there is a rhyme and reason to this. So what we get when we expand on this is we're going to get 1 over V naught is equal to Km all over Vmax times the substrate concentration plus substrate concentration all over Vmax times the substrate concentration. All we did was expand this fraction out into two separate fractions. Any questions on this so far? I know some people, right? Fractions. It's been a hot minute. I get it. I don't want to lose anybody. So if you're not sure what just happened, say your piece. We won't make fun of you. I won't, at least. Okay. Everybody good? I wish there was like an emote thing, like a thumbs up kind of thing, so I get feedback right off the bat. All right. So if you get lost in the sauce, feel free to say your piece, and we'll kind of slow it down and backtrack. Okay. So the next step is really just we're going to kind of do a combination of both simplifying and expanding. Okay, so we're going to kind of condense two steps into one by simplifying and expanding at the same time. So we're going to simplify certain aspects, simplify, and then we're going to expand other aspects of this. So for instance, right off the bat, we can simplify by crossing out this substrate concentration on the right-hand side. And so we get 1 over Vmax because the S is concentration, the substrate concentration will cancel out. And here's the bit. Okay, so I want everybody to pay attention right here. Okay, I'm not doing any kind of crazy math magic, but I'm going to multiply this Km by 1, right? So this does not violate any math rule. Km times 1 is still Km, okay? Km times 1 is still Km, okay? So this is within math legality, I don't know. Okay, we didn't violate anything here, but this is the trick that you need to pay attention to, okay? Now, when we do this, the next step we can expand on this. So we got 1 over V naught. And now what we're going to do is we're going to take this fraction, this first fraction we're encountering here, this Km with the red multiplication of 1. We're going to make that into two separate fractions. So we're going to get is Km over V times 1 over the substrate concentration. Right? So all we did was take that first fraction and expand it out again, and that's what we get. And then the last piece is plus 1 over Vmax. Aha, we did it. This is now, it may not seem like it, but this is, and the Y is equal to mx plus b format. That straight line equation we learned back in, I don't know, middle school, elementary school, okay? And this is known as the Lineweaver equation. This is the Lineweaver equation. So why do we get through all this, right? This tear-jerking moment in our lives, okay? Probably some yawning going on. So the reason why we did that was because for the MCAT, unfortunately, we need to know both Michaelis-Menten equation and the Lineweaver equation. Now, if you're really high speed, right, and you can follow this math, guess what? That makes your life a little bit easier, because if you just know Michaelis-Menten, guess what? You can derive very quickly the Lineweaver equation without brute memorization of two complex equations, right? So really, this is going to save you a lot of time and struggle and heartache and whatever else, okay? But you will need to know both the Lineweaver equation and Michaelis-Menten, unfortunately. So that kind of sucks, right? Just one more thing we have to remember. And so throw this on a note card. Put this on an Anki note card. Be able to do this. Just do this a couple times. Get a whiteboard out, piece of paper. Just do it, 3-4 times, and it should be second nature. I promise. Okay. So let's draw a Lineweaver. So we drew the Lineweaver equation, the Lineweaver-Burke equation. Let's draw what the Lineweaver plot looks like. And so this is simply, well, you're just going to draw an XY plot. Too easy. Your coordinate plot. And you're going to draw a reference line here at an angle. And when you draw this line here, this black line at an angle, at a slant, okay, this is the kinetic of the enzyme, just the enzyme of itself, okay? And you want to make sure that you kind of have this triangle here in the plot, right? So where the slanted line meets the plot behind it, you want to have this nice little open area of the triangle. Okay, and this will be obvious here later when we draw the enzyme with the inhibitor. Okay, so we want to know three points. We want to know 3 points on this plot, on this Lineweaver plot. The first point we want to know, it's not really a point, not a true point, is the slope. So based on the equation, we know the slope of the Lineweaver is just going to be Km over V max. Okay, easy enough. Km over V max. The Y-intercept is what? Anybody? What is a Y-intercept?
One over V max.
Yeah, it's 1 over V max, right? That's the B. That's the letter B. Good, excellent. So that's just 1 over V max. And then the X-intercept we didn't talk about. Not yet. So we're going to do a little bit more math. Okay, and this will be the last piece of math we're going to do, I promise you. And then I'm going to show you guys how to cheese this. Okay, so you don't have to do all this crazy math. Okay. So first we got to do the lane way before we can get kind of fancy with it. So we're going to solve for the X-intercept. Does anyone remember how to do that? Let me solve for the X-intercept.
Make y equal 0.
Yeah, good. So if we've got y is equal to mx plus b, all we got to do is we got to turn that y into 0, nothing, nada, zilch, and then we just got to solve for x. That's all we're going to do. We just got to solve for x. So our x, right, it's just going to be x is going to be equal to, well, we're going to move that b to the other side, so we get a negative b, and then we're going to divide that by m to isolate the x. Okay, so that's our framework. So let's do that with that convoluted Lineweaver equation. Let me rewrite that real quick. So 1 over v naught, let me do that in black, be consistent here, or ish. 1 over v naught is equal to Km over v max times 1 over the substrate concentration plus 1 over v max. Okay, so that is in the same form. That is y equals mx plus b. Okay, but let's simplify that. So we said y, the y term needs to be zeroed out. So in this case, the y term for us in this convoluted equation, this Lineweaver equation, is 1 over v naught. So we're just going to take that, we're going to set that equal to 0 right there. Boom. Same deal. To simplify this as well for us, we're going to say this 1 over s, or x right here, the third term, we're just going to say, let's just call that x for simplicity. Okay, that's what we're solving for. This x is what we're solving for. Let me circle that. Okay? And then we're just going to rinse and repeat what we did before in the simplified version above. So we're going to try to solve for x. So x is going to be equal to, well, we're going to take this 1 over v max here on the far right-hand side, and we're going to subtract that to the other side. So we get a negative 1 over v max. And now we're going to divide this term, this Km over v max, the m, right? And all we're going to do is we're going to divide this out. When we divide this out, we just flip it to the other side. So what was on the denominator is now going to come to the numerator. Okay? And then we can cancel out the v max. And what we get for x is simply negative 1 over Km. So our x-intercept, mathematically, this point here in the far left on the plot, is negative 1 over Km. So let me stop there for just a second and make sure everybody's on the same page. Does anybody have any questions on that? I know sometimes dividing fractions, people might get lost on that. Okay, so if you need me to do it the long way to show you how Vmax was on top and how we cancel Vmax, that's fine, let me know. But I want to make sure everybody's on the same page before we move on. And I promise you, this is the last math-heavy stuff. Okay. Okay, so I'm going to assume everybody's Gucci. If not, I'll stick around later and you can ask me questions in private. Feel free to always ask questions, right? We're not here to shame anybody or make you feel intimidated to ask any questions. Don't feel that way at all. So let's, what we're going to do is we're going to slightly ahead and then I'm going to bounce back up and help you understand some of these, how to achieve some of these things. So the first thing we need to talk about is what Km and Vmax are. And we need to simplify this even more. Okay, we need to make it really dumb, right? The dumber the better. Okay, so we said, oh yeah, Km is equal to 1/2 the Vmax, right? As we talked about above in the very top here. We said, oh yeah, Km is 1/2 Vmax, cool, fine. And then we went on to say, yep, Km measures affinity, fine. And then we said, well, and I said, that's all fine and dandy. So let's even make that even dumber, right? Let's make it as dumb as possible. And so the first thing I want you guys to write down on this is that Km, at least the way I want you guys to think about Km, is that instead of thinking of it as a measurement of 1/2 Vmax or affinity, I want you to think of it as hugging distance. Hugging distance. Oops, that's a gnarly G. Hugging distance. Hugging distance. The distance the enzyme travels to hug its substrate is known as the Km. Okay? Humor me. Sounds a little weird, but there's a point to this. So, the next thing you need to know about enzymes is that once they've hugged, right, once they've hugged their substrate, the next thing they do is they turn that substrate into product. And that's in fact what Vmax measures. So Vmax, right, simply put, you can think of it as substrate to product turnover. Substrate to product turnover. So when you think about enzymes, they really just have two functions, right? First, their first function is Km, which is to bind or hug, right? They walk to the substrate, they hug it, and that's known as the hugging distance or Km. So Km is the first thing that enzymes do. The second thing that enzymes do functionally is Vmax. Once they've hugged that substrate, okay, they just simply turn it into product. And that's what's known as Vmax. Okay. So this is keeping it very, very basic, very, very simple to not over convolute this. Okay. So with that in mind, you can think of this as Km first, right? That's the hugging thing, hugging the substrate. Once it's hugged, it performs Vmax, which is substrate to product turnover. So let's go back up and look at this plot and see if we can kind of help us cheese this just a little bit. So the way you can remember the slope on this plot, okay, this Km over Vmax, is simply that it's just the functional order of how an enzyme works. Okay, so first, right, Km is the hugging distance. That's when the enzyme hugs the substrate. And then once it has the substrate, it simply turns it into product, substrate to product turnover, which is known as Vmax. And so the slope is really just functionally 1/2. Right? It's just a chronological order, a list of how enzymes go. 1/2. That's pretty simple. Okay. So that's how I achieve that, how I remember the slope of a Lineweaver graph. Next, right, when we think about this Y-intercept, we notice that the Vmax is in the denominator. Fine. Well, so I just say, okay, because both these terms, both the Y-intercept and the slope, the way I've drawn it, right, they're both in the same quadrant. They're both on the right-hand side. And because they're both on the right-hand side, they both have the same denominator. They both have Vmax in the denominator. Okay, fine. And then I say, wait a minute, what about Km? Km is on the numerator for the slope. But when we switch sides of the y-axis, right, as soon as we switch sides to the negative, because it's negative, we flip everything. And now the Km is on the bottom. Okay? So this is how I kind of cheese it, but you have two ways, right? And maybe you have other ways to remember this, but this is how I go about it. And this has been really successful with a number of my students, okay? So I'm guessing the math is not going to be very popular. It's not very popular with me either. And so I try to find ways to cheese this, how to memorize these three quote-unquote points, okay? And you will need to know these 3 points for the MCAT. You will need to know the slope. You will need to know the Y and the X-intercept. You will need to memorize this plot. Okay? So maybe screenshot it, put it on an Anki deck, and practice it, because it's that important. You can't just do 2. You need to know all 3 of these. Okay? Anyways, enough of that. So, 2 functions of an enzyme. I want everybody to write this next piece down as well. This is a cardinal rule, and this is super, super, super important. Super, 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 super important. Did I mention what's super important? Okay. And this is the cardinal rule of enzymes. So they put a little red asterisk here to denote that. And I want everybody to internalize this right now. Vmax. Only. Let me highlight that because it's that important. Only changes when there is allosteric binding, or if there's an allosteric site. What is an allosteric site? Anybody?
A binding site away from the active site.
Yep, perfect, beautiful, cool. I like it. So, Andrew, I'm gonna pick on you. When does Vmax change? When is the only time Vmax changes?
Vmax changes when there's like maybe an inhibitor.
Nope. Written down right in front of you. What does it say?
Okay. When there's allosteric binding. Sorry.
Yeah. I want everybody to read this. I want everybody to say this out loud, basically. You don't have to unmute yourself, but read this out loud and say it out loud and really internalize this. Vmax only changes when there's allosteric binding. Okay? Period. It's as simple and as dumb as that. Don't overcomplicate this. Vmax only changes when there's allosteric binding. Okay, I'm going to quiz you guys on this here in a moment to see how many of you guys retain that. Okay? But you're right, Andrew. Because we're talking about inhibitors, Vmax is always going to go down. If there's an allosteric site, and because we're talking about inhibitors, it's always going to go down. Okay? If there's allosteric binding, it will go down because we're talking about inhibitors, period. Okay? Internalize this. Okay. So what we're going to do now is we're going to draw out competitive inhibition, non-competitive inhibition, and uncompetitive inhibition. Now, you guys might be saying, well, Kevin, what about mixed inhibition? Well, the problem with mixed is that it can take on the characteristics of any of the 3. Okay? So it's going to be kind of like that Frankenstein's monster, and you don't know what you're going to get. Okay? So if you know the first 3 that I mentioned, then you'll be good when you see mixed inhibition. Okay? So today I'm not going to talk about mixed inhibition because it's pretty low yield on the MCAT. But if you know these 3, you're going to be good to go. I promise. I pinky promise. Okay? We can seal it with a thumb, with a kiss, or whatever. I'm not going to lead you guys astray. So, competitive inhibition. Let's write that out. And what we're going to do is I'm going to. My app is. There you go. Now it's responding. I'm going to write out the name. We're going to talk about a good definition. We're going to draw it out, okay? And then we're going to graph it out, okay? So we're going to be very thorough on this process. So, competitive inhibition. Competitive, what a word, inhibition. Can everybody give me a layman's definition of competitive inhibition? Anybody, for 1,000,000 points.
It competes with the substrate.
Good. What does it compete the substrate for? Competes for the
binding
site, or what's the name for the binding site?
Active site.
the active site. Okay, competitive inhibition means that the inhibitor competes, hence the name competitive, competes for the active site. Pretty straightforward, right? No mental gymnastics here. For the active site. Makes sense. It's in the name. It's pretty straightforward. Okay, so let's draw this out. So I'm going to draw first what normal looks like. Okay, and there's a reason why I use hugging distance, and it'll be very obvious here in a moment because we're going to relate a lot of stuff to hugging. So hopefully you like hugging people. Maybe not now with COVID, but you know. Anyway, bada bing, bada boom. So let's draw an enzyme, and the enzyme, it's got little arms, right, on each side. Okay, and if you were to, maybe put a head on this enzyme, maybe put a head, right, from the top down, from an eagle view, kind of looks like a person, right? There's their head and there's their arms on each side. Okay, so the enzyme looks kind of like a person. Okay, this analogy will kind of help us out. So this enzyme, right, sees a substrate, chilling, S, substrate, and it's going to have to travel, it's going to have to walk some distance to hug this substrate, right? And what is that known as? What is this action called? This hugging distance, what is that called? Yeah, it's Km. Good, excellent. Yeah, so Km is the hugging distance. Is the hugging distance. So the distance the enzyme has to travel to hug its substrate. Okay, pretty simple. Good. All right, so this is normal. Let me label that on the bottom here. Normal situation. Normal. Cool. That's what we want to happen, right? This is a healthy relationship. Okay. Let's talk about when we got an inhibitor. Do you, just in chat real quick, in the voice one chat, do you guys have any siblings? Do you guys have an older sibling, younger sibling? Post it in chat real quick while I draw this out. Because you got siblings, you're going to relate to this quite easily. This next picture. So here's an enzyme again. It's a little bit larger than last time. That's okay. So let's pretend, right? We said, well, this enzyme could be a person-ish, right? Maybe put a little head on there. And let's pretend, got a younger brother, two younger sisters, two younger brothers. I like that. I like you guys have younger siblings. Okay? Awesome. So you guys are going to relate to this really, really well. So let's imagine this enzyme is your grandmother. Okay? Grandmother's in town. She got gifts. Okay? You're her favorite. Your grandma's favorite. Okay? So you're the substrate. Further up a little bit. So there you are as a substrate. Your grandmother sees you. She's coming towards you. And then, right, your younger sibling, your shithead younger sister or brother, can be kind of mean here. Okay? Comes in, swoops in, and tries to take that hug away from you, from grandma, right? Says, nope, I want that hug from grandma. I don't want you hugging grandma. Okay? And so grandma comes up, she's walking. She sees your little brother or sister coming up, trying to intercept that hug. Says, nope, not today. She stiff arms your little sibling like a QB, a quarterback, okay, and walks right around your brother or your sister to give you a hug, okay? So I'm being a little bit crude for a reason, because I'm trying to do a little bit of comical effect. I'm trying to have you guys remember this, okay? I'm not trying to be mean, promise. And so what's happened? What happened between the original, the normal, on the left-hand side now? Well, we could say that the hugging distance, right, increased. The hugging distance increased. So our Km went up because grandma now has to walk further than she did before, right? She has to walk around your sibling to get to you, okay? So that's one way to remember that. Now, let me pick on somebody else. Redstone, let me pick on you. Vmax, what happens to Vmax? What happens to Vmax? Are you sure? Why does it say the same? We'll talk about that here in a sec. But that's not, Vmax has nothing to do with saturation. Well, per se, yeah. Not in this example. Okay, let me hop into it. Good, excellent. Yep, that's that cardinal rule I was talking about, right? So if there's no, is there an allosteric site here? No, there's no allosteric binding. So if there's no allosteric site or binding, guess what? Vmax does not change. It's as simple as that, you guys. Okay? There's no allosteric site, Vmax doesn't change. That's that cardinal rule. Vmax only changes when there's allosteric binding, period. Okay? Vmax only changes when there's allosteric binding. Simple as that. So Vmax, there's no change. Okay, so when we graph this out, when we do our Lineweaver plot, right, we're going to draw our plot. It's going to be our default setting, right? We're going to draw this every single time, and I still do this whenever I see these kind of problems. I'm going to draw my slope out. Slope is, Andrew, what is the slope?
It's Km over Vmax.
And how do you remember that?
Kind of just remembered it.
Okay. Well, you can also remember it based on the chronological order that enzymes operate, right? They've only got two operations, right? First, they hug, which is known as Km. Once they've hugged, they turn substrate into product, which is called Vmax. So it's just 1/2. That's all that is. 1/2, chronological order of the activities that an enzyme does. Too easy. Okay. All right. Clueless. What is the Y-intercept?
Km.
1/1?
Sorry, it's 1 over Vmax.
Good. Excellent. How do you remember that?
It's just, since it's on the same side, it's 1 over that. Yeah.
Awesome. Like that. And Clueless. What is the X-intercept?
It's -1 over Km.
And how do you remember that?
It's on the opposite side, so it's all reversed.
Flipped over. I like it. Cool.
Yeah.
Fantastic. Don't forget the negative, right? Good. Excellent. Simple as that. Simple as that. Okay. You guys are doing great. Okay. So now what I'm going to do is we got to evaluate each one of these three terms on this plot to see what's going on. So we said Km goes up, right? We said Km goes up. So that goes up and Vmax stays the same. So when we look at the slope, when the Km goes up and the Vmax stays the same, what does that mean? Well, that means there's more rise character. So our slope is going to be somewhere up here. We don't know exactly where, but we just know it has more rise character. It's simple as that. And then the next term, the Y-intercept, we said, okay, well, Vmax stays the same, right? So it doesn't change. So this term stays the same. So the dot goes right on top. And then we said, well, Km goes up for this last term, for the X-intercept. And so if the denominator goes up, right, the denominator increases in value, and then the overall value actually decreases. Not only does it decrease, but it's negative. So it's a smaller negative number, and so the dot might be somewhere right there. And guess what? Now we just connect the dots, and we just drew competitive inhibition. Okay, easy, easy, easy. Okay, let's do another one. Let's talk about this saturation business that Redstone brought up. Okay, I don't typically talk about it because it gets kind of confusing, but let's talk about it. So you may be asked on an MCAT question, how would you reverse a competitive inhibitor? And the answer simply is, well, you just add more substrate. Okay. So if we had this situation, we have an enzyme, and we added a 1-to-1 ratio between the substrate and the inhibitor. Technically speaking, right, all things being equal, the probability of the substrate binding or the inhibitor's binding would be 50-50, right? There'd be a 50-50 chance for either substrate or the inhibitor to actually bind, realistically. So what you can do is you can put those odds in your favor. And so all you would do is that you would just add a ton more substrate to increase the likelihood that the enzyme always binds to the substrate instead of the inhibitor. So instead of having just one 1-to-1, Let me put 1 to 1 below this enzyme above the 50-50. If you had something like 1,000,000 substrate to 1 inhibitor, well, what would those odds be? Right? If you had 1,000,000 substrate, I can't draw 1,000,000 substrate. Right? A ton more substrate compared to 1 inhibitor. Well, you basically drown that inhibitor out. It becomes almost invisible, right? Because the likelihood is that 99.9999999% of the time, the enzyme's gonna interact with the substrate over the inhibitor. And so functionally, the inhibitor gets drowned out and is no longer quote unquote present. Okay, it's just so minute that it doesn't matter. You've drowned it out. You've diluted it too much to have any impact. Okay, and that's what Redstone was alluding to. Cool. Any questions on competitive inhibition up to this point? Okay. Hopefully I'm doing a good job. So now that we talked about competitive, let's talk about non-competitive. Non-competitive inhibition. Awesome. And MCAT account 95. What would you think? Could you give us a definition for what non-competitive inhibition means? Any ideas on that?
It has equal affinity for the active site or the allosteric site.
Not quite.
For the inhibitor?
Yep, for the inhibitor, not quite.
Okay. It can bind the allosteric site, but I also thought it could bind the active site.
Nope, that would be mixed. Non-competitive.
I thought non-competitive was a special kind of mixed where you have equal affinity for both.
So non-competitive is a type of mixed inhibition, absolutely correct. For the purpose of the MCAT, though, assume that it's separate from mixed, okay? So we're looking for a simple definition of non-competitive inhibition. So you're right, the enzyme does have affinity for both the substrate and the inhibitor, and we'll talk about that in picture here soon, but I'm looking for a simple definition of what non-competitive inhibition means. So, John, what do you think non-competitive inhibition means?
Is that me?
Sure.
It binds allosterically to the enzyme and doesn't allow the substrate to go in.
Yeah. Okay. Fair. Okay. So maybe I'm not asking this question right. What I'm looking for. You guys aren't wrong. Okay. Neither are you, MCAT, account 95. Okay. But what I'm looking for is a very simple definition. Something simple. And if I'm looking for is non-competitive, means that it's non-competing. Non-competing. And so if it's non-competing, that means what? It's not competing, right? It is not. The inhibitor is not competing for the active site, right? If it's not competing, well, what does that mean? Well, it's not competing for the active site. So if it's not competing for the active site, what is it binding to? Well, if it's not competing for the active site, it's binding to another site other than the active site. That's called an allosteric site, right? It's binding to an allosteric site. So let's draw that out. Let's draw out what that looks like. Draw our enzyme again. Okay, since we know by definition the inhibitor is non-competing, right? It's non-competing for the active site. We know there must be an allosteric site. So let's draw that out. Let's hotbox this in red in the back, right? Let's draw our substrate. There's our substrate. Let's draw our inhibitor. And so we know the inhibitor has its own site, right? It's got the back door. It doesn't care about what's in the front. It has no interest in the active site. And so the enzyme, right, can still bind to the substrate, okay, with its active site. So the substrate can bind to the active site with no problem because the inhibitor is happy with its own site. It doesn't care, right? So Km hasn't changed. The Km, or the hugging distance, hasn't changed. Km hasn't changed. What has changed is the Vmax. And clueless, why has the Vmax changed?
Just this allosteric binding.
You nailed it. Nailed it right on top of the head. Exactly right. So Vmax, the only decreases or only changes when there's an allosteric site, so it goes down. Okay? So this would be akin, let's pretend this enzyme maybe is your dad. Okay? This enzyme, your dad's coming up to you, you're the substrate, your dad's coming up to you to give you a hug, okay? And your little brother jumps on the back of your dad as he's approaching you, starts choking him out with his neck, right around his neck, his arm around his neck. What has happened there? Well, your dad might be slowed down, right? The Vmax might be slowed down, but the distance between you and dad hasn't changed. Yeah, your dad might be a little slower to get there, but the distance between you and dad hasn't changed, despite your little brother hanging off your dad's neck. Okay? So Vmax only changes when there's an allosteric site. Simple as that. The hugging distance between a substrate and enzyme hasn't changed at all. So let's graph this out. Let's put this on the plot. Let's draw that out real quick. Our reference plot. MCAT at count 95, what is our slope?
Km over Vmax.
Good. And how do you remember that?
You could derive it like you did, or just memorize it.
Yeah, good. And what is the Y-intercept?
Y-intercept is 1 over Vmax.
Good. Excellent. And what is the X-intercept?
-1 over Km.
Killing it. You guys are doing great. Fantastic. All right. So let's evaluate each one of these terms real quick. We said that Km stays the same, and then Vmax goes down. So in this case, the denominator decreases in value, and then the slope must also increase, right? The overall value must increase. So we just put a dot up here. 1 over Vmax, well, we said Vmax decreases, so that goes down. And so that the dot must be above as well, somewhere. And then the Km on the last term, we said stays the same, so the dot must intersect right on top. And then we just connect the dots. So I recommend this method quite a bit, okay? Do it this way because if you try to memorize non-competitive with competitive, you may get it mixed up on the test. And that would be a dumb mistake to make, okay? I know a lot of people have ways to cheese these plots and try to remember it. I don't recommend it, okay? All right. Any questions on non-competitive inhibition? Okay. All right, let's move on then. Let's do the last one. And the last one's going to be uncompetitive. Uncompetitive inhibition. Can someone give me a simple definition for this? Right, correct. Yeah. So the inhibitor can bind to an allosteric site only when the substrate binds first, right? It's the binding of that substrate that will create this pocket, this allosteric site. So to make this simple, I actually like to think about uncompetitive as being a compound word. And the way I choose this, because you got like non-competitive and uncompetitive, what the heck is the difference? So what I want you guys to do is potentially focus on this word un. And the way I think about this un is simply that un is going to be the word for undulating. Undulating. Does anybody know what that word means? Undulating. Anybody look this word up and tell us what it says? What does the word undulating mean?
Having a smoothly rising and falling form or outline. That's what it says online.
Yeah, and so typically the word is used to describe wave-like motion as well, right? So like how a flag gets caught in the wind, okay? Or in microbiology, it might be used to describe the movement, the caterpillar-like movement of certain microbes, that inching, right, forward. Okay, so let's write that out. So this undulating means, right, it's going to be this wave-like movement. And what we can actually do is we can also give this an alternative definition as well. Specifically, right, we could say that this is a change, right? This wave-like movement is really a change in shape which facilitates movement. So this un, I want you guys to try to think of this as undulating, maybe expand our vocabulary just a little bit, okay? And if we know that this un refers to this wave-like movement or this change in shape which facilitates movement, then we have a big clue, right? We have a big clue on what's going to happen. And so let's draw this out and see if we can figure this out. So we said earlier, right, that uncompetitive inhibition is when the substrate binds. And when the substrate binds to the enzyme, it produces this allosteric site for the inhibitor to bind. So let's draw that out, okay? So let's draw this enzyme out. So there's our enzyme. And you can almost think of this as undulating competitive inhibition, right? By the name, it's kind of like, the first half is kind of like competitive inhibition. We have this enzyme and this substrate. And what's going to happen is this enzyme is going to go through this hugging distance, and it's going to bind to the substrate. That's known as Km, right? I think we should be fine with this hugging distance analogy. And then from there, what's going to happen is when this substrate binds, I'll write this out as well, but when the substrate binds, it's going to form this allosteric site. So let's draw that. Draw that. And I'm going to put these arms of the enzyme a little bit closer together to show that it's binding. And here's the substrate inside. And let's draw a little pocket in here as well. So when the substrate binds, it produces allosteric site that the inhibitor can now bind to. Let's write that out. So we have this note. When the substrate binds, it forms an allosteric site. Okay. So we're not done quite yet. When the inhibitor binds, what's going to happen is that this enzyme is going to do like that death hug, okay? It's going to do like that grandma hug where it's really, really tight, suffocating, okay? It's going to be kind of like this stuck lock and key, okay? And so what we're going to do is we're going to draw this with the inhibitor now bound and show the difference between the middle picture and this picture we're going to draw. So the arms of this enzyme are almost kind of like pretzel around and squeeze. It's going to squeeze this substrate. Okay, it's going to squeeze it really tight into its active site. So I want you guys to pay attention to something real quick. Notice, so I'm going to call this center picture, a normal hug, a normal enzyme hug. This is normal hugging, okay? And imagine real quick that you were hugging somebody else right now. Let's visualize that for a moment. And think about the last time you gave somebody a hug, and maybe visualize you looking down at your feet. And what do you notice? Well, you notice that there's a little bit of distance between you and the other person. And that's true here as well. There's a little bit of distance when somebody gives a normal hug between the substrate and the enzyme, right? We still got this little bit of gap here in blue between the substrate and the enzyme. Okay, so this is like a normal hug. There's a little bit of space, right? You're not touching pelvises. But when the inhibitor binds, we get something called the death hug. The death hug or the grandma hug, right? When grandma comes sees you, right? It's not just any hug. She's going to squeeze the life out of you. Okay. When you get a grandma hug or whatever, you look down at your feet or whatever, there is no space between you and grandma, right? This is the death hug. And this is what's happening here, right? There is no distance between the substrate and the enzyme. And so when we look at this successively, the Km, what do we notice? We notice that the Km, the hugging distance, went down. Okay. And what happened to Vmax? What was that cardinal rule? Clueless?
It changed because there's allosteric binding.
Yeah, and it changed in what way?
It decreased.
Bingo. Perfect. Nailed it. Chef's kiss. Mwah! Okay. Fantastic. So let's draw that out real quick. Let's draw a plot again. And John, are you there? Nicole, are you there? Thunder, are you there?
Yeah.
Okay, what was the slope?
It was Km over Vmax.
Good. And the Y-intercept?
The Y-intercept should be 1 over Vmax.
1 over Vmax, good. And the X-intercept?
-1 over Km.
-1 over Km. Perfect. Excellent. So let's evaluate these three terms real quick. We said, well, Km goes down and Vmax goes down. So for the purpose of the MCAT, assume that the amount each one of these decreases by is the same. So they're the same magnitude and decrease. Okay. Same magnitude and change. Okay. So in effect, they kind of cancel each other out because they're the same amount. Okay. So in this case, the slope didn't change. The slope is exactly the same. Right? So what does that tell us? That tells us that with the inhibitor, the slope is going to be the same, and it's going to run parallel. Okay, we just don't know if it's going to be above or below. So let's evaluate these other two terms to see what it is. So Vmax, we said, goes down. If Vmax goes down and the Y-intercept, that means this entire term goes up. And Km, if it goes down, well, that means that this term on the x-axis is going to be larger, but it's going to be a larger negative value. And so because it has the same slope, the slope didn't change, it's going to run parallel right above. And just like that, you were able to draw all three of the inhibitors: competitive, non-competitive, and uncompetitive. Okay, so this is a difficult topic. I'm not going to sugarcoat it. Okay, so I'm going to send you guys these notes if you forward me your email, and rewrite these notes. Go over this a couple times. Okay, my students typically we write these notes and teach it or talk it through a couple times, 2 or 3 times before they have mastery. Okay, and that's what I mean, mastery, because my students get these right every single time. So make sure you draw these out a couple times and really understand what these look like, these mechanisms, until you can see them in your mind's eye. Okay, really understand what Km and Vmax does, and if you can do that, then you can quickly draw this out on a plot without any trouble. And so these are going to be like gimme points. So when you see this on the MCAT, you're going to put your hands up together, you're going to look up in the sky and say, thank you, MCAT gods, for giving me free points. Now, you will get 90 to 95% of these problems right. Okay. And so the next thing we're going to talk about is how to kind of fill in the rest of that. And the rest of the enzyme kinetics is a little more advanced, okay? Don't want to scare you guys, but there is some equations you do need to put on an Anki card and memorize. So, there were some of these on here. The first one that you need to know is catalytic efficiency. Does anybody remember the equation for catalytic efficiency at all?
Is that I forgot it. Vmax equals Kcat times E.
Ooh. Close. I like where you're going.
It's
So efficiency.
I think it's. Sorry.
Oh, go ahead. No, go ahead. Keep going.
No, I thought it was. I think it was Kcat over Kd.
Ooh, close. Very, very close. You guys are hot. Okay, so it's actually going to be Kcat over, not Kd, but Km. Very, very close. And the way I memorize this equation is that, well, the word cat, right, shows up on the top twice. So cat and catalytic efficiency, and then Kcat, right? They're both on top. The other one that I really like, that a student actually told me about, is that, well, you kind of think of Kcat and Km as Kcat over K mouse, cat and mouse, right? So whoever is more efficient, the cat over the mouse, and the cat is a little more, because it's an apex predator, it's going to be above the mouse. Okay, so that's one way you might be able to choose that as well. The other equation you need to know, and we've already talked about this. Well, let me draw another dot. The other equation you need to know is Km, right? We talked about this earlier. We said that Km is just 1/2 the Vmax, so throw that on a note card as well. And then the last one you need to know is Vmax. What is Vmax technically, right? So I give you a simple definition that is just the substrate to product turnover earlier, right, for the sake of simplicity, but now we want to kind of expand on that mathematically. And really, what this is Vmax is technically Kcat times the enzyme concentration, okay? And Kcat, by definition, is what we wrote earlier. Kcat is just the substrate to product turnover. Is the substrate to product turnover. Or you could say this is a fraction, substrate to product turnover, okay? But Vmax technically is Kcat times the enzyme concentration, or substrate to product turnover times the total enzyme concentration. So make sure you have these three equations on a note card, because they will come in handy for those last 5% of problems you might see related to enzyme kinetics. Okay. All right. So let me go back up, because I told you at the very beginning I was going to go back up and show you guys another way to remember Michaelis-Menten. Okay. So Andrew, you're still there. I didn't ignore your comment. Okay, I was just saving it. You asked me, well, what does that double reciprocal mean, right? I think you may have asked that in the chat as well. Okay, that's a good question. So what it means is that Michaelis-Menten and Lineweaver are reciprocals of one another. Double just means that you reciprocate or flip over each term on either side of the equation, right? Doesn't matter what side of the equation we're at, of the equal sign, you just flip them both over. That's where the double is coming from. So if we know the slope of Lineweaver is Km over Vmax, right? We know that's the functional order of how an enzyme works, okay? This Km over Vmax in magenta and yellow, 1/2, right? That's Lineweaver. All we got to do is flip that. We got to flip that, and we get Michaelis-Menten, right? So instead of being 1/2, it's simply going to be 2/1, right? Because they're reciprocals of one another. 2/1. Okay, so now Michaelis-Menten hopefully is a little bit easier, because now, well, you know what? You know it's the big booty equation. So we have that plus sign in the denominator. Okay, that's why the denominator is expanded out. And now we know that Vmax is actually on top instead of Km, because this reciprocal, or the opposite of Lineweaver, makes it a little bit easier. Okay. Okay, so I do have some problems ready to go. Let me see if anybody needs to ask any questions, and then we'll try to do these questions with passages right after. So are there any comments, questions, or concerns relating to this lesson? Okay. Take that as a no. And Red, could you do the poll thing again as well? Okay, so let me try to paste that into the chat, the voice one chat. So there's one picture. Let me paste the other picture. Okay. So here's the first problem. I pasted in the voice one text channel. And let me go ahead and paste that as well into this diagram or this document so we can work on it together. And maybe I'll zoom out just a little bit so we get everything in frame. Maybe slightly bigger. Okay, everybody can see this just fine? Already got somebody answering. You guys are saying D on that one. Okay, we'll see. We'll see. We'll see. Let's work it out. So I think this problem has a lot of utility to this. I think one thing I like about this problem is that it forces you to convert between Michaelis-Menten graphs to a Lineweaver plot. And even if you do get the right answer, I think this is also nice to have to really kind of challenge you to see if you can identify all the other graphs, what they might be. Okay, so let's go through this process real quick. It shouldn't take us that long. So this first problem says the initial velocity V naught of an enzyme catalyzed reaction at different substrate concentrations S is shown below. Which graph best represents the corresponding Lineweaver plot? So when we look at this, what do we notice? We notice, right, the V max without the inhibitor decreased with the inhibitor. So we can simply say that V max has decreased. So V max goes down. But we also can see that Km, right, just like in the problem I showed you guys earlier, that Km stays the same for both. So Km did not change. Km on the x-axis is still the same. So Km did not change. So based on the lesson we just talked about, you should be able to narrow this down, right? We know that Vmax only changes when there's an allosteric site. So right off the bat, we know it cannot be a competitive inhibitor, right? In fact, if we want to challenge ourselves, this would be a non-competitive inhibitor based on these characteristics of Vmax and Km. So this is non-competitive. And all we're going to do now is simply draw this out. So we're going to draw our reference graph again. We're going to draw the 3 points that we need to know. So the slope is Km over Vmax. The Y-intercept is simply just 1 over Vmax. And then the X-intercept is a negative 1 over Km. And then we just evaluate. Simple as that. So Vmax, so Km stays the same. Vmax goes down. So that means we've got a dot further up. It's become a rise character. Vmax goes down. So that means this dot's going to be slightly up. And Km didn't change. So the dot stays on top. All we got to do is connect the dots. Okay, and of those graphs, which one follows suit? Like you guys said, it's D. So that's the correct answer. Awesome job. Everybody got that right. Cool. What is C? Can anybody tell me what C is on this graph? What is C?
Uncompetitive.
So this is non-competitive. C is what? Uncompetitive? Yep, it is uncompetitive. Good. You guys are destroying this. What is A? Yep, Andrew's on top of it. I like it. A is mixed. And what is B? B is competitive. Okay, right? And if you're not sure, well, just think about what that mechanism looked like, right? So with competitive, right, we said what? We said the Km value goes up, right? Because that's when your little brother is trying to steal that hug from your grandmother, and your grandmother like linebacks your little brother to come at you. Okay, so she increases her hugging distance. So Km goes up. Vmax doesn't change at all because, well, there's no allosteric site. So let's draw that out. So again, we draw 3 dots, right? I'm not going to belabor this too much, but we got Vmax, Km over Vmax, that's M. Vmax goes up. Or excuse me, Km goes up, Vmax stays the same. So we got a dot further up. Good. And then the next dot is just simply 1 over Vmax. And Vmax stays the same. So that dot stays the same right there. We have 2 dots right now, right? We could stop right there and just draw a line. The line just requires 2 dots, and there's your competitive graph, and that would be B. Okay, so this is a quick way to check yourself if you're not certain. Awesome. All right, so let me put another question up. Question up. And this is, let's see here. And put the question on here first, and then I'll paste it into the chat so you guys have access to it. And I may just make this bigger, so give me 1 sec. Let me increase the text size, maybe to, let's do 18. I think that's a good size here. And I'll paste this in the chat as well. Thank you, Red. Appreciate it. Man, Thunder, you're on it. Man, you're just clicking all over the place. Are you guys sure it's A? Okay. Who was stuck on this one? He was kind of like, I don't know what's going on here. Andrew, okay, a little bit stuck. That's fine. All right, let's talk about this then. So, a proposed drug, let me center this just a little bit. Okay, yeah, this one's a little bit more difficult, but I think it's going to make sense pretty quick here, okay? You're going to have this moment, you're going to be like, oh, of course, okay? So, actually, let me do this. Let me stop there real quick. Of the people who picked A, who wants to try explaining this first?
I will.
Okay, let's do it. Awesome.
So what gave it away for me is it says structural analog, which makes me believe that it is very similar to the substrate of this enzyme, which makes me believe that it would be a competitive inhibitor.
Yeah. So can you explain what a structural analog is again?
Oh gosh. I think it's just like it's structurally very similar to the substrate.
Yeah, it's similar in, let's say, shape, I guess, similar in shape to a substrate, right? It mimics the structure of a substrate. That's the point of a structural analog. And why would you want something to be similar in shape to a substrate? And just like Nicole said, it's to mimic that substrate so it can compete for the active site. Awesome job. So I compete for the active site. Okay. And based on that right there, we know we're dealing with a competitive inhibitor. Aha. So, what do we know about competitive inhibitor? Andrew, what happens in competitive inhibition? What happens to our Vmax? What happens to Vmax during competitive inhibition?
Sorry, I'm having a little brain fart right now.
When does Vmax change?
When there's allosteric binding.
Yeah, is there allosteric binding with
Yes.
competitive inhibition?
Yes.
There is? Are you sure?
Oh no, there isn't. Sorry.
Right? In the pictures we drew, there is no allosteric site for competitive inhibition because competitive inhibition competes for the active site. It doesn't need an allosteric site, right? It's already competing for the active site. So there's no allosteric site. So therefore, Vmax does not change. Simple as that. So does that help us? Let's see. Some of the answers we can rule out. So if we look at A, B, C, and D, we can see that, well, D says it decreases when it shouldn't. It should stay the same because there's no allosteric site. So basically, B, C, and D, we can automatically rule out because it says that Vmax will decrease when in reality it should stay the same, right? So based on that logic, that rationale, right away, we can get to A, which is the right answer choice, okay? And based on that, too, we know that for competitive inhibition, Km, based on what we drew out, right, that hugging distance increases when you add inhibitors. So A is the correct answer in that regard. Nice job, Andrew and Nicole. Thanks for volunteering and speaking up. I think I have one or two more. You guys are doing fantastic. Let me do this one. Let's do a little passage-based one, just one question that's based on a passage. And let me paste this here first, and then I'll paste it into the sub chat. And let's see how I want to do this. I'll do it like this for now, and then I'll try to. One sec. I missed the question stem. Let me put that in here as well. And then let me copy and paste all this and paste it into the chat. Oops. Let me do the ordering is a little off here. Apologize. So the passage below the answer choice in the question stem in this case. So give that a read and then see what your answers are. And Red, let me see if I can do the same thing. I guess I can just copy and paste that, yeah? Red? There you go. What do you guys think? All right, so I think that's most everybody. We're missing one more person or so. How do we feel about this one? No idea, okay. No worries, Thunder, we can talk about it. Red, a little bit of trouble here. Okay, so let's talk about this a little bit more. So this is a prime example where you don't need to read all of the text to understand what's happening. So if we focus on the question stem, it asks us which of the Lineweaver-Burke plots shown depicts the inhibition of topoisomerase B by camptothiosin, right? And so first we understand is, well, what kind of inhibition does camptothiosin have? And so we're told in the second paragraph towards the end there, the third line or the fourth line in the second sentence, that camptothiosin is a non-competitive inhibitor, right? I'm going to highlight that in yellow. And so right here, you got to think back and say, okay, when we're talking about non-competitive inhibitors, what does that mean, right? What did we say non-competitive inhibitors were? Well, they were non-competing. Specifically, they're non-competing for the active site. So automatically, we got to think of allosteric binding, right? So the KM didn't change, but because we got an allosteric site, right? Whenever we have an allosteric site, Vmax decreases. From there, all we do is we graph this, right? We draw our default plot with a reference line. We put in our three little dots, slope, Km over Vmax. And then we put our Y-intercept, which is just going to be 1 over Vmax. The x-intercept is going to be negative 1 over Km. And then we just evaluate. Simple as that. So Km stays the same. Vmax goes down. So we know our dot goes up. 1 over Vmax, we said that goes down. So the dot goes up. Km stays the same. So the dot goes right on top. We connect the dots. Okay. And so we kind of figure out, okay, which of those fit in that? So of that, right, the only ones that actually fit is going to be C and D. Okay. And so we got to figure out, okay, well, what is the difference between C and D? And it looks like the difference here is what's on the X and the Y axes, how they're labeled, right? So I think I may have failed to mention this earlier, but you want 1 over the substrate on the X-axis. So you want the X-axis is always 1 over the substrate. Just like Michaelis-Menten is the substrate on the X-axis, but we do the reciprocal, so it becomes 1 over the substrate concentration. And then just like Michaelis-Menten, right, the velocity will be on the Y-axis, but it'll be 1 over because it's the reciprocal, right? Lineweaver is reciprocal. And so C is the correct answer choice compared to D because D has these axes mixed up. Okay. Cool. So does anybody for 1,000,000 points know what A is? What kind of graph A is? What is A? Is A competitive? Is it non-competitive? What is it?
Competitive.
It's competitive, yeah. And so if you really want to try to cheese this too, and I don't necessarily recommend this, just because I think it's really important to elaborate on these 3 points, the slope, the x-intercept, and the y-intercept, and so forth. But if you're really hurting, and again, I don't recommend doing it this way, but you could say, well, if you look at this, this forms like an X, right? This forms like an X. These two lines form like an X. And so you could think of this as the X games, and the X games are competitive. So that's one way you might be able to cheese this, but that's kind of like level 1 stuff. You really need to be up here where you evaluate all 3 of these points, the slope, the X, and the Y-intercept. Okay. So that's one way you could do that. Awesome. Thunder and Redstone, does that make sense?
Yeah, that makes sense.
Cool. All right, so apologize for being a little bit crude earlier, right? Talking about your little brother or little sister in a mean way, but I did that for dramatic effect, trying to make sure that you guys can kind of remember some of those talking points, right? So I'm big on emphasizing certain things to make them stick in your head. So, later tonight or tomorrow, you're like, oh, wait a minute, I remember Kevin making a big deal about this, okay? So it's just for dramatic effect. Not a mean guy, I promise. Okay, but hopefully that worked. If it didn't, well, I'm sorry. Maybe I'll do better next time. But hopefully this was a good review. And again, typically my students go through these notes 1 or 2 times with their study group or on their own and draw them out. And most of my students typically get 100% on these kind of enzyme kinetics, right? So there's utility and power in reproducing these notes one more time, okay? And it looks like a lot of you guys did really well, okay? And if you guys are still struggling with this topic after a couple of days or so of reviewing, feel free to reach out to me, okay? It's not a problem at all. I want to make sure that you guys do really well on enzyme kinetics and other sections of the test, okay? So reach out. If you're still struggling with this, that's not a problem at all. Are there any questions, comments, concerns, insults? I take them all, okay? That's going to be it for me. I'll stick around for another 10, 15 minutes or so just to answer some generic questions you guys might have. Could be about this topic or other stuff too, right? So if you're struggling with something else, maybe I'll be happy to answer that as well, or try to.
I have a question. Do we ever discuss KD in enzyme kinetics?
So KD is a measurement of dissociation. I typically don't.
Oh, so that's okay.
Go ahead.
So it has nothing to do with dissociation of the enzyme and the substrate or anything.
No, I mean it does, but for the purposes of this, I think this review, I didn't want to get into that too much, where we start going like E goes to S, and that makes the enzyme substrate complex, and we go backwards as a dissociation KD, and all that kind of like reverse forward reaction stuff. I'll be frank, I'm probably not the one to best talk about that stuff. I think, if you go to like Chem Library, that website online, they do a good job reviewing that, probably better than I could. Okay, so I don't want to waste your time or mislead you. It's not something that I focus on. It's not something I've seen a lot of questions on either on the MCAT. So,
okay.
Yeah, but I know what you're talking about. Okay, KD, you may see that in relevance to or in reference to enzyme kinetics, but you probably will see KD also in like chemistry. Okay, the dissociation constant as well. So, a great question. Yeah, look into it, but I don't think it's super high yield for the MCAT. I'm trying to keep this as high yield as possible.
Okay, thank you.
Yeah, and I can maybe try to find you a link too that covers that pretty well. Any other questions?
Can you send me the? Did you have notes on the optics class last time? Because I missed it.
Yeah, sure. So I could send you those notes. I just want to preface that we did it both visually using this app, and we also did it mathematically. And I think there's utility in doing it both ways. So you can